Oh, not here.
There's no okay.
Thank you very much, Chapman University, Andrew, Sarah, all this distinguished group. I feel really extremely privileged. By some perhaps coincidence, we were celebrating two events. Now we are celebrating Yakir Aharonov's 91st birthday, and a few months ago we celebrated 30 years to the Elitzur Weidman experiment. And we thought to take this opportunity to give this talk about the letter, about the Elitzur Weidman bomb testing experiment, but under a special frame. As a matter of fact, Yakir Aharonov and myself are preparing an online course on quantum mechanics. This is a very ambitious project because we want the course to be at both levels. On the one hand, it should be a popular course such that everybody, even people who never studied science, can understand it and get deep into the mysteries of quantum mechanics. And on the other hand, it is going to be an academic course that students can get credit for, and we are preparing it on both levels such that both populations, both kinds of people can enjoy it. So this is the name of the course, to be or not to be a quantum. This is not the question. And this time I'm going to concentrate on the Elitzur Weidman bomb testing experiment. Why do I want to do it? First, I like it. I was fortunate enough to be one of the co-discoverers. But there is another reason, and this is that I think that we can take interaction-free measurement as a very good introduction to the world, to the magical world of quantum mechanics. That is, if you want to explain quantum mechanics to a layperson and show them how beautiful this realm is, I think with all modesty that the interaction-free measurement, or as people like to call it, bomb testing experiment, is a very good introduction, and it is for you to see. So what I'm going to do, there will be no mathematics in this talk. This is for the general public, although there is a lot of mathematics behind it that everybody can later grasp and learn. But what I'm going to do is to explain some very basic principles in physics, one or two, and then based on these to go into quantum mechanics. So I'm going to explain, to begin with a question that actually has been a huge controversy in the history of physics about something which fills this world and fills our life. What is light? So you know the guy on the left side, Isaac Newton. He is the greatest founding father of classical physics, and he had a very clear opinion, what is light? And he said light are small particles coming from the candle, from the lamp, or from the sun. And because he was the founder of classical mechanics, he said these particles, which are very, very tiny, they behave according to the laws of mechanics. They go in straight line, then they impinge, they hit all kinds of objects, and then jump to our eyes just by the same angles that tiny balls would do. So said Newton, and he had very good evidence for that. He had very good reasons to do that. He said light is particles. There was another guy, and probably both of them went to the same hairdresser, and it was Christian Huygens, who had another opinion. He said light is not particles. Light is akin to something that we know, say sound. Light is waves. And now these two gentlemen argued, and each of them had his own reasons to support his view. And to make a long story short, how did classical physics eventually accept Huygens' opinion that light is wave? So here's a very simple notion that I'm going to introduce, and this is interference. There is something very nice about waves, and this is that when waves merge together, they merge in a very interesting way. So I'll assume that these are waves at the same wavelength, and here is one possibility. Imagine two waves coming together and they have the same wavelength, and they are in phase. That is, the ups and downs, the troughs and the crests are just facing one another. In this case, they will strengthen one another. This is in phase, and we will have interference. The resulting wave is going to be twice as big just by this constructive interference between the two waves. And then there could be destructive interference, such as they come out of phase, this waves up facing these waves down and vice versa. As a result, they are going to just obliterate one another, and they will be canceled. And of course, everything can happen in between. Here you can see a very simple demonstration with water waves. Here you have a wall with two openings, and then imagine a flat wave coming from the left, then giving rise to diffraction, that is, the waves disperse, and then they meet each other, these two small waves, and they give rise to interference in the sense that in red, you can see the constructive interference, they strengthen one another. In gray, they cancel one another. Here you can see it even dynamically as a GIF. That's all very simple. Now, a man named Thomas Young, genius who was an expert in many fields, he conducted what is considered to be the most beautiful and simple experiment in the history of physics, the interference experiment with light. He simply shed light on a partition where there were two slits, and then there was a screen behind this partition. Lo and behold, you have places where light is stronger and where there is actually no light. Now, what could those particle people say? So, we have guests, welcome.
Thank you.
Let us sit here so that you can see the presentation.
Oh, is that the presentation there?
Oh, yes.
Good. But then we have to have you behind us. You
Oh,
at
yeah.
the back of our head. Why don't you stand over there? Then we can see your face as well as the presentation.
But he's got to press the button on the computer.
Ah, that makes
You're going to have a lot of exercise turning your head from here to here.
You guys consider over here.
Just imagine I'm watching tennis.
Very good. I also love it.
Gotcha.
So here is, okay, so this is interference once again. So remember, waves can strengthen one another. That would be constructive interference. They can cancel one another. That would be destructive interference. Everything in between, as you saw with the water waves, and then even dynamically. Cool. Along came this guy, Thomas Young, and said, here what I did. I shed light on two slits, and there was a screen behind, and lo and behold, you have light and dark, light and dark. And now, if you want to support the particle theory of light, you may feel a bit ridiculous, because you will have to assume that these particles attract one another or repel one another. In time, as optics and electromagnetism became more and more advanced, then it turned out that you can actually calculate and predict exactly what will be the intensity of light at every point on the screen. You can do that. You can try this at home, because you would need the monochromatic light, not the light that we have from the lamps. But if you have light which is only red or blue, then you can do that. But here is where you can see interference in the ordinary light. Take soap bubbles. So the membrane of soap is not at the same width everywhere. So some of the wavelengths cancel one another and others strengthen one another. So this is how you see all these beautiful colors. So light is waves, no other way. Until 20th century came, and this good man made a revolutionary discovery, and he found out that there was to matter and to energy. What do I know about matter? Here is the podium. I know that if I break it into half water and then keep breaking it all night, I'll come to a piece of matter which cannot be broken anymore. It doesn't have half, third, either 0 or 1 or 2. People thought earlier that these were atoms, then they discovered particles, then nowadays they talk about quarks. But we are accustomed to the fact that matter is discrete, that you can break it infinitely, but there is a unit of matter which has no half or quarter, but either 0 or 1. Planck found out that energy has a similar property, that is that when you break energy to, say, light to its smallest quantities, you come to a quantity of light in which you cannot divide it to a half. You can't have something smaller, either 0 or 1. And then along came this guy who was 26 and sent to Planck. Planck was the editor of an important journal, and he sent him within a year 4 or 5 papers. You know that editors usually send papers to referees, and if referees say to publish it, if they agree or if they do not agree, there is a way for the referees to decide whether a paper should be published. And Planck was a very good man, and when he saw these papers, he said, "I've never heard about this guy, and I have no doubt that if I send these papers to referees, they will reject it. They will recommend to reject it. So I'm not going to send it to referee. As an editor, I'm making a decision to publish it." And the amazing thing was that this anonymous guy quoted Planck in order to do something that actually wreaked havoc on classical physics. What did Einstein say? He said, I propose the following experiment. Here is a source of light, and here in this jar, there is a gas. So these circles are the atoms or the molecules of the gas. And now I'm going to shed light on the gas, and you know what happens to something on which you shed light? It gets heated, which means that its molecules begin to rapidly move. Then said Einstein, I'm going to make, just as Planck said, I'm going to make the source dimmer and dimmer and dimmer and dimmer, so dim until we shall have this quantity which Planck said that could not be divided. What is going to happen to the gas? Let me promise you that if you walk out of this talk, or if you turn off your screen, you will not regret it. And if you continue to listen to this talk, you may be very miserable. Because here is what Einstein says. I'm going to make the source so dim that it will emit only 1 quantum of light. And then I'm going to wait for a while, because it turned out that the behavior of this quanta is probabilistic and not deterministic. You can only say what is the probability that this quantum will be emitted at this moment and where it's going to hit. And then Einstein found out that 1 molecule, 1 atom, only 1 is going to get a push. How much energy was hit this molecule? Of course, by Planck, we know that it can't be less than a quantum. How much energy was emitted by the source? Also quantum. And who, after 200 years, is laughing from his grave at Westminster? Waves. How could it be a wave if all the energy, everything hits on a single atom? And actually, Einstein said something even worse. He said that this quantum of light will just take out, knock out a single electron from an atom. So imagine, you think that an atom is something very small, but imagine atom being as large as the Colosseum, then the nucleus will be some marbles that you hold in the middle, and the electrons would be mosquitoes just flying around this Colosseum. So they are the smallest thing that you can imagine. And this guy Einstein made a calculation and showed that you need all the energy of this quantum of light in order to knock out this electron. And he actually made a calculation and gave a prediction, and people went and tried it and said, Einstein, you discovered a new effect. What do you do to guys who discover a new effect in physics? You give them, as you know, you give them the Nobel Prize. What did Einstein do when he heard that he got the Nobel Prize? He didn't attend. He sent somebody to take the money because he was offended. He said, I hate quantum mechanics. You should give me another Nobel Prize, which they never gave him. But we are returning now to our problem. And the problem now is really severe. Interference shows that light is waves. light gives rise to diffraction, that is, it goes to a slit and then it goes around, it can go around objects. Light gives rise to interference, as you have seen. And then comes a guy and gets the Nobel Prize for showing that light is actually a particle. So gave name to this particle. They say we have electrons and protons, so why not call them photons? And here's the problem. Let's begin again with classical physics, so it's not going to be difficult. I'm going to emit a ray of light into a half-silvered mirror, and there I have two detectors there. So let me explain what is a half-silvered mirror. Suppose that the light hits a transparent glass, then it will all be transmitted. If it hits a mirror, it will all be reflected. That means that if it's a half-silvered mirror, then it will be half transmitted, half reflected. You split the ray of light into two halves. Everything is fine. But now, what happens when you go quantum? And as Einstein likes to do, you make the source dimmer and dimmer and dimmer until you have a single quantum of light. So here's what you're not going to have. You can't have half a photon, just as you can't have half an electron, half a proton. It is either transmitted or reflected. So what do you do now? There is no half photon. Then comes Born and says, here is the rule. You can't talk about intensities because there is no intensity weaker than a single photon. So you have probabilities. Just repeat the experiment many, many times, and you find out that exactly 50%, in 50% of the cases, the right-hand detector clicked, and in the other 50%, the left-hand detector clicked. Just to see whether you understand it, suppose that it's not a half-silvered mirror, a quarter-silvered mirror, then you understand the probabilities would be different. But the probabilities actually come exactly, precisely, instead of the intensities. So far, everything is nice. But now, how do you explain it? For Einstein, it was clear. And here it is. Einstein said, consider the time between the moment that the photon is impinged on the half-silvered mirror and the time in which one of the two detectors clicked. Where is that photon? Einstein said, simple. It's either on the right or on the left, on its way. It has been either transmitted or reflected. We don't know, just as we don't know when I flip a coin, I don't know whether it is heads or tails. So it's 50%, 50%. But actually, it is not 50%, 50%. If it fell and I didn't look at it, it is either heads or tails. The moment I look at it, I understand, I perceive something which is objectively there. Anything simpler than that? Einstein is a guy who is very logical. And then comes his friend Bohr and says, forget it. You didn't want to get the Nobel Prize, you didn't want to receive it, but you should understand what you said. It's a superposition, Einstein. And the particle is superposed over both paths. Yes, Einstein, it was both transmitted and reflected. It went into two opposite ways. Yes, the same photon. And only when it reached the detectors, then it decided to materialize on one side and vanish from the other, or the other way around. So here it goes. It's in a superposition. It's both. It goes on two opposite directions. Then you make a measurement. Once you make a measurement, recall the conservation laws. You can't get two photons from one or zero photons from one, so you should get only one. So either this one clicks and it's only here and vanishes and collapses, as some people say, and vanishes from the other place, or the other way around, that you make a measurement and it's here and it collapses. And Einstein hated it, of course, because he said that quantum mechanics is becoming crazier and crazier, and he wanted to show that this is all wrong. Here's an interesting story. In the dialogue between Einstein and Bohr, it's a long story, but you better read it about it somewhere else. These were two gentlemen who loved each other immensely, but they differed sharply about quantum mechanics, and they used to give each other hell with Gedanken experiments. Einstein was very good in that. In these days, technology would not allow performing these experiments, so Einstein said, let's just imagine them. And now, let me stress, every such Gedanken experiment, which is a German thought experiment, is nowadays a Gemachten experiment, an experiment which can be done and is done even in this university. So said Einstein, and here is the interesting thing. These two geniuses, Einstein and Bohr, immensely loved each other, and they were so clever that every once in a while, Einstein said, I know what Bohr is going to say. And Bohr said, I know what Einstein is going to say. And they tried to anticipate one another. And when both of them became old, it was actually a scary scene to see the two of them talking. Nobody understood them because each of them was trying to go into the brain of the other. So this is how it happens, that when Einstein saw Bohr, he said, Bohr, here's your next argument. It was Einstein who gave Bohr his next argument. And then he tried to refute it. And he said, you're probably going to propose that rather than placing two detectors, we shall place two mirrors, this time solid mirrors. And here we place another half-silvered mirror. And here we place two detectors. Don't worry, I'm going to explain. We have two half-silvered mirrors, two solid mirrors, two detectors. Now what are we going to get? Let me show something simple again in classical physics, which is very beautiful. So here is again this Mach-Zehnder interferometer, two solid mirrors, two half-silvered mirrors, and the two detectors. Imagine a wave. Yeah, you have to turn, this is a technical term that you have to flip the upper half-silvered mirror. Now imagine that there is a wave in classical physics, and this wave can be split into two halves. Notice by the laws of physics that the reflected half is having its phase shifted. Now the two halves are meeting the two solid mirrors, and then they approach the second half-silvered mirror. This half is split into two quarters. This half is being split into two quarters. It happened at the same time. I just separated them. And now you can see that these two quarters cancel one another. So they don't give you half, but zero. And these two quarters strengthen one another. They don't give you half, they give you one. That is, again, the interference that we have shown earlier. Light gives rise to interference. And in this Mach-Zehnder interferometer, you can see it very nicely. And here it is. Each ray of light which is entering this diamond shape of mirrors below from the left is going to emerge to the right. It will just continue its direction. Let me see if you understand it. If it comes from the right, it will go out to the left. So you have two detectors, and if you don't do anything and you let light enter it, it will continue on its way to one of the two detectors according to the way it entered the interferometer. And now comes the problem. Now again, let's do what Einstein likes to do and make the source dimmer and dimmer and dimmer until you have a single photon every few minutes. What you're going to have, now we don't have intensities, we have probabilities. Lo and behold, but these probabilities are very strange probabilities because they give rise to a very unique physical phenomenon. Light will always, the single photon will always emerge on be detected on the right-hand detector, never on the left, which tells you that in some very strange way, each single photon has taken both paths. This makes Bohr very happy. And now you can understand why this is so distressing. Because should we place two detectors, we will never detect half a photon. Either there will be one here and zero there, or 1, 0 here and 1 there. But now it turns out that we shall never see interference. If we remove the two detectors, once again, we shall see interference. How can we explain that? And let me just tell you that if you think that this is the problem, this is just the beginning. Everything that I say here with photons will be the same with electrons, neutrons, protons, atoms, molecules, the same schizophrenia, the same duality of wave and particle plagues both matter and energy, both energy and matter, and this is quantum mechanics. Now, how can we understand that? As I said, I was privileged and lucky to do my PhD with Yakir Aharonov, who together with his mentor, David Bohm, have discovered the Aharonov bomb effect, which actually shows that even an electron, you don't have half an electron, but you can show that an electron went through two slits and even does something really amazing, that is sensing something which goes within the solenoid. It's a different story. But how can we understand the fact that we don't know which path the photon has taken? And this is the important point. If we don't know which path the photon has taken, the photon itself doesn't know which path it has taken. And in some very crazy way, it's going to take both paths. In order to understand that, we have to go to this young genius of quantum mechanics who have found the uncertainty principle. And it says something very nice. Think about a classical object, say a projectile, say a bullet that you shoot, or you throw a rock, and then it gives you this, this parabolic trajectory. At every moment, you know exactly, you can tell exactly the position of this object and its momentum, that is, its velocity times its mass. Not so, say Heisenberg, with particles. You can tell exactly the momentum of the particle when it moves, but that is the velocity in a certain direction. But then you don't know where it is. It is, as you see, like a wave. It resides in many places. You can say, no, I don't like this. I want to know exactly where it is. No problem. Here is where it is. But it has several momenta, which is really crazy. It's at a certain point, it has a precise position, but it has many momenta. This is the uncertainty principle. And then says Bohr to Einstein, you have to understand this problem of the single photon interfering in the light of Heisenberg's uncertainty principle. Yeah, I don't know if this is correct, but this is what people say that should be engraved on Heisenberg's tomb. So then said Einstein, tell Bohr that I found a way to disprove the uncertainty principle. I understand that if I place two detectors on the two paths, I'm killing the detector. Then I will never see interference. So this is a manifestation of the uncertainty principle. I have to choose whether I find out which path it has taken, but then I will never see its interference. Or if I remove the two detectors, then I will not know which path it has taken, but I will see interference. That's another manifestation of the uncertainty between position and momentum. Said Einstein, why not? We can imagine a detector which is so delicate that it will not absorb the photon. It can just get some kick from it. If you think about electrons or neutrons, then it's easier to understand that. So it will only indicate whether it went from the right, whether it took the right path or the left path, and then I will see interference. So here is a falsification of the uncertainty principle. Bohr said, let's try it, and he calculated it. I'm not going to show the calculation, just I'm going to show it visually. Indeed, in half of the cases, in 50% of the cases, the right-hand detector is going to click on the interferometer, but then interference is destroyed. Rather than having this nice pattern of 0 and 100%, I'm now going to have 50-50. And the same in the other 50% of the cases. The left-hand detector is going to click, and once again, interference is destroyed. If you want to see interference, just remove the two detectors, and then you will get nice interference again. Do you understand that? Everybody who says I don't begins to understand quantum mechanics. And here it comes to the thought that I had some 30 years ago. It was Thursday, and the next day was Friday, and all libraries in Israel were closed, and I had to think about it for a whole weekend, and it drove me nuts. I was thinking about this experiment, and I knew that if you don't measure which path it has taken, then interference will be such that always it will emerge, it will emerge to the right-hand detector. But I know that if I place two detectors which will delicately sense without killing the photon, whether it took the right path or left path, I'm going to destroy interference. This is known. And then a thought occurred to me. What happens if I give up one detector? From now on, my life became very miserable. Because here it is, in 50% of the cases, the detector will click. So then I have a which path information. I know its position, which means that I'm destroying interference. Everything is fine. But what about the other 50% of the cases where the detector remains silent? Now, do I know where the photon is? Don't hold your breath. I mean, conservation law says that if there is one photon and it can be in one of two paths and it's not on the right path, it must be on the left. So I have certainty about its position. Now, will interference be lost in the case it is silent? Well, I should say that I never received the Nobel Prize, and be assured that I would receive the Nobel Prize have I shown that interference would not be destroyed in this case, because then I'm actually violating the uncertainty principle. I know that it was on the left, and still I'm seeing interference, which Einstein hoped so much to gain. So I assumed that I'm not going to get the Nobel Prize, but then I understood that I'm going to get something very nice. Think about it. The detector is on the right. We place it there. The photon went on the left because the detector never sends it. How come that when the photon comes out to the two detectors, it somehow responds to the presence of the detector? In other words, it can sometimes go out into the left final detector. For comparison, just to show you how strange it is, suppose that the detector's battery is off. Will there be a click? And will I get information about the path taken by the photon? Don't hold your breath. There will be no click. Come on, this is quantum mechanics, but there is no battery. And of course, I have no information about the photon, where the path it has taken. So interference will remain intact. But in the other case, in which the battery is there and there was a silence, interference will be destroyed. You understand this? I have two cases of silence. One silence because the detector cannot click, and then interference is not destroyed and the photon always goes to the right. And the other case, the detector could click, but it did not click. Just by this could, the photon emerges and sometimes in 50% of the cases go to the left. So we have to distinguish between two kinds of silence. To the classical one, where we have no battery, we should give a name in physics. I propose to call it simply nothing. But we need to have a more subtle name for the case in which there is silence, there is no click, but there could be click. We should give it another name rather than nothing. How about, why not call it Gornisht, which is Yiddish for nothing? So we have to distinguish between nothing and Gornisht. Garnisht, you want to speak German. And if you think that this is just fun, here is what we thought to make it more dramatic. Replace the detector, the single detector, by a bomb. And this bomb is so sensitive that suffices that a single photon goes next to it without even being absorbed by it, and your photon will explode. Now you want to know whether the bomb is good. So suppose that some of your bombs went wet and you are selling them to the army. These are very good bombs that can kill terrorists if they smoke very far away by a single photon that this comes from the cigarette of this guy at night, then it can kill it. So you send it to the army and you make a lot of money. And now it turns out that some of the bombs are wet and rusty and you don't know whether they're good or not. So you want to test them. One way to test them is just to take a laser pointer and just shine on one after another and say, this is not good, this is not good, boom, this one was good, but of course you're not going to like it because you're going to all your remaining bombs. And then came Weidmann and myself and said, place a single bomb in this interferometer, what you are going to have in 50% of the cases, it's going to explode. So you know that the photon went on the right, and you say, too bad, I know that that was a good bomb. But in the other 50% of the cases, it will not explode. And in 50% of these 50% of the cases, just as you saw in the earlier slide, the photon will go out to the left. So this is a good bomb. You can be sure about it. What is half out of half? This is 1/4. So here is the achievement, something that you can never do in classical physics. You have a bomb or an object which, by definition, the slightest interaction that you make with it will change it. And you want to know whether it can change. We made it dramatic by making it a bomb. You want to know whether the bomb can explode. But if the bomb is such that the slightest interaction known to physics is going to detonate it, then forget it. You can tell whether the bomb is good or not just by destroying it. And now you can see that 1/4 of the bombs, you can be sure, something that quantum mechanics, the classical mechanics does not allow you to do, you can be sure that it's a good bomb. Okay, we saved 1/4. What about the other quarter? I mean, in some of the cases, the right-hand detector is going to click. So you don't know whether it was a nothing or a Gornish. Because if the right-hand detector clicks, it's either a no good bomb and there was no interference, or it's a good bomb, but it goes to the left only in half of the cases. No problem, just send another photon, hide somewhere, and again, half of the photons at this round are going to explode, the other half are not, and from this half, so you have 1/4 of a quarter, you just repeat the experiment, and now you can add to your quarter 1/16. What about the other 1/16? To make a long story short, then it goes to 1/64 and all that. They all add up to 1/3 of the bombs that you can make sure that they are good without wasting them. Then came Weidmann and changed it by playing with the efficiency with the transparency of the mirrors, rather than 50-50 to 3/4 and 1/4, as I showed earlier, and we raised it to 1/2. And later came Zeilinger and added the Zeno effect, which I'm not going to describe here, and brought it very close to 1. We sent this paper to some of the best journals: Nature, Science, Physical Review Letters, Physical Review. Most of them rejected it by the editor. They said it's such a silly idea, we are not going even to send to the referees. And then it was the 5th journal that accepted it. But meanwhile came Anton Zeilinger, who later received the Nobel Prize, and he realized it, he made the experiment. And about the same time before the paper even was published, Sir Roger Penrose, who yesterday gave it publicity in his book, Shadows of the Mind. He described this, you remember this, this beautiful drawing of his. And of course, we were very happy when he received the Nobel Prize. Why do I think that this is important? I believe that the IFM, rather than being just an amusement, first of all, there are numerous technological advances made on the basis of the interaction frame measurement. But first I want to go to the theoretical one. And I want to say that quantum mechanics is unique. We know how it differs from classical mechanics. We have the wave-particle duality, we have non-locality, which we are going to discuss in another lecture. There are some features of quantum mechanics which makes it different from classical physics. But here is one thing which I believe is very fundamental. As we say in Yiddish, if grandmother had wheels, she would be a wagon. In classical physics, that's meaningless. Grandma has no wheels, so she's not a wagon. What quantum mechanics says, if you have a quantum mechanical grandmother, and she could have wheels, then in some cases, even if she has no wheels, she could outrace a police car. So we have shown it in a series of interesting papers with some applications. And I want to stress, sometimes people, sometimes my students say, oh, So now I know I'm not going to specialize in quantum mechanics. It's going to make you frustrated for the rest of your life, all these riddles that you cannot understand. So I tell them, first of all, there is a lot of money there. There is a lot of industry. Much of the technology today is based on quantum mechanics. When you use a transistor, you're actually making use of the wave nature of the electrons. When you use quantum communication, in cases where you don't want people to listen to you, so this is the kind of this technology which people nowadays invest millions. Quantum communication is immune to eavesdropping. Think about, and here we go to something very interesting. Think about, first of all, I want to mention the importance of this use of quantum mechanics. Think about the Hungarian cube. When you want to solve the Hungarian cube, why is it so difficult? It is so difficult because sometimes you have to go back. You make some errors, you make some erroneous moves, and then you have to switch it back and then begin. So you understand that your possibilities immediately split into 2, 4, 8, and this is what makes it difficult because you have to go back and forth. Suppose that I have a Hungarian cube which is quantum mechanical, and suppose that I myself am quantum mechanical. So every time that I have to make a decision, I don't make a decision. I just split into 2 with my cube. I make both moves, and then the 2 of us split again into 4 and into 8 and so on and so on. Make all the moves. How long do you think it will take until one of those thousands of players would say, got it? Very little. This is what quantum computers are aspiring to do, rather than by trying by trial and error to take one possibility and then another and then another. How about trying all of them together and by certain quantum mechanical magic akin to this interference, get the solution without trying all of them one after another. I'm very proud of this achievement that Eli Cohen and myself produced a paper with Ibrahim Karimi, how you can use interaction-free measurement for medical purposes when you make, say, CT scans of people, how you can get very accurate pictures with a minimum of radiation. And I'm closing to the end. So here's something so important to all of us, and it has something to do with what I mentioned earlier about quantum computers and about the Hungarian cube. You all ate either breakfast, lunch, or dinner, or you're going to eat after this talk. You better. You're going to take carbohydrates, which is the way you get energy. This energy comes from the sun. This energy comes from the sun, but we can't get it directly from the sun. If you stand in the sun and get the energy, you're going to die. The only way you can get this energy is to eat something which has carbohydrates, which are coming from the plants, and these carbohydrates store the sun's energy. What is a carbohydrate? Say, what is glucose? It's a very simple molecule, but 6 carbons, 12 hydrogens, another 6 oxygens. Very simple. And how do you do it? You take carbon dioxide, which is just waste coming from your breath. You take water, which you have everywhere, and you take light. How come that nobody ever managed to produce a single carbohydrate molecule? Today we play with DNA, we play with proteins, but nobody can produce a carbohydrate molecule, although you have all the carbon dioxide and water and light that you need. Every little grass outside is doing this thousands of times in a cell every minute. Very likely, photosynthesis is attained by taking advantage of the quantum mechanical nature of light, and absorbing the chlorophyll is very likely absorbing light from many places. And rather than playing with the 2 molecules of the carbon dioxide and water, one possibility after another, very likely this is what the chloroplast is doing, somehow trying all these possibilities together, and once it gets a molecule, it stops and begins anew. And then, is it possible to go further? Can we outsmart the uncertainty principle? Who said yes, we can? You know this guy. And who did it? So this is again Yakir Aharonov, who showed a very interesting way to outsmart the uncertainty principle, and for this he got the White House medal. And what Aharonov is doing is the following. He said there is something very strange about the quantum mechanical interaction. We know that when I send a photon, there is uncertainty. I don't know where the photon is going to end up. I have a wave, and I have to wait for what people are calling the collapse. That's everybody know. Said Aharonov, why don't we take the final state of the particle and then run the calculation backwards? We are going to get two calculations, two wave functions. In classical physics, they are redundant. They repeat one another. In quantum mechanics, lo and behold, they add up to one another. And then you find, I would say the following. Just as quantum mechanics is amazing when compared to classical physics, Aharonov's formalism, although it is completely identical with the quantum formalism, just this new way of thinking is just as radical revision of quantum mechanics as quantum mechanics was to classical physics. It turns out that God plays dice in a very strange way. The dice is random not only by the way it is cast, but by the way it is going to fall. The dice is subject to influences from both past and future. And it brings me back to the bomb testing experiment. So you remember the Mach-Zehnder interferometer, in which the photon goes on two paths, after the half Hilbert mirror, goes two paths and then comes and becomes united back. Lev Weidman found a slight variation of this experiment, which he called the nested interferometer experiment. And there he found out something very interesting. He employed Yakir Aharonov's method of calculating things backwards. And what he got in this case, as you can see on the right, there is a detector D1, which does not click. So we may think that this is a detector to which the photon never went. Wrong. It turns out that the wave function coming back from future to past, going through this small interferometer within the large interferometer, gives rise to a momentary particle just within this section. Do you understand how crazy this is? The photon never went to the left. The photon never came back to the left. But at a very brief time, the photon existed within this path. Is it possible that this is what is happening every time that there is an interaction-free measurement? We think that nothing went to the bomb, but we understand that there was some strange interaction because the photon, although it went through the other path, somehow reacted to the presence of the bomb. Is it possible that what Weidman has discovered, that in some cases you could see that there was a particle and then a negaparticle going together? So you think that there is nothing there, but you can split them for a very brief time and see that your nothing is actually a particle and negative mass particle going together. I know that it sounds to you very strange, but here is a paper in Nature Scientific Reports, which we published together with two Japanese guys. The experiment has been carried out recently. And what I want to say is that the two-state vector formalism is nowadays opening to us a completely new realm of physics, which is extremely exciting. Phenomena like negative mass or negative energy, which we thought do not exist in physics, can be shown to play a very important role in this mysterious world, which may enhance our better understanding of it. Which leads me to the last reflection, which is again due to Aharonov. Yakir, who, as I said, celebrated his 91st birthday, has a lifelong obsession. Do we have free choice? And he is working on this day and night. For him, it is very important to show that when we make a decision, when we make a choice, we are not bound by our past. What science tells us is that every time that I make a decision, a moral decision, every time I make a choice, I am enslaved to the past. What quantum mechanics can offer me is that there is some random quantum mechanical processes going in my brain. So this doesn't give me free choice either. There is a very interesting idea by the two-state vector formalism due to Aharonov, and this is that if within our brain processes going on both directions of time, then perhaps we do have free choice. Suppose that I can cancel, just as I showed earlier, that I can cancel something in my past, in my very early, my very close past, some neuronal event in my brain. So that in some way relieves me from being a slave to the dynamics of my brain and giving us some very genuine sense of freedom. I am talking hesitantly at this point because this is a very new idea, not due to me. It is to Yakir to explain it, but I can promise you that it is extremely exciting. And just as Penrose believes that quantum mechanics can explain to us phenomena like genius, like music, like art, like intuition, it looks like that even the question of free choice, of free will, has something to do with it. So in some way, God plays dice also in this divine interaction between him or whatever power and us human beings. Once again, I wish to profoundly thank Chapman University for making these events possible. Thank you very much, Andrew. I wish to thank the president, Daniel Strope. Thank you very much, Sarah. Thank you all. It's been a real pleasure to be here. And quantum mechanics is such that if I give this talk, say, a year later, it will already be different because things are happening always. New things keep emerging. So it is a
The
great.
bomb might have gone off.
There you go. Yeah, bomb can wait and gone off, and some other bombs can come. So once again, thank you very much. The stage is for you for questions.
Did Anton Zeilinger ever do the experiment?
Oh, sure. That's the interesting thing. The paper was not yet published. The news came from Vienna. The Zeilinger who got, we are old enough to remember that there was a time in which there was no internet. You remember? Oh, you're too young for that. But there was a time in which we put papers in envelopes and sent them by mail. That was that time. So Lev sent, he was frustrated that it is not going to be published. So he sent it by mail to all the world. And then the news came from Vienna that Zeilinger performed the experiment. It was not yet published. I think that was one of the reasons why the fifth journal, Foundations of Physics, agreed to publish it. It said, I mean, whatever the referees say, the experiment has been done. So Zeilinger was the first, and let me say another thing. He improved it by adding the Zeno effect, which I did not describe here, which is familiar to you. So he raised the efficiency. We began with 1/3, raised it to 1/2, and he raised it to close to 1. So it is Zeilinger.
And where did he publish his paper?
Where we were rejected, physical review letters. And it was immediately accepted because he came with them. Yeah. We've been through this a few more times with a nested interferometer and with all, we had this being rejected, and then people say, no, we knew that you were correct, but there was this and that problem. Fine. We have some more innovations coming.
So, picking up on Roger's talk this morning, so we've got these two paths, and maybe so sometimes the photon is there, sometimes it isn't there, but its its presence makes a difference. So I suppose the gravitational difference is going to be very small for photons.
Sure.
But if you do this with molecules, is this a way of testing this claim?
That's a huge question because here you have Penrose on one side and Zeilinger on the other side. So Zeilinger says, and they have opposing view on that. on the measurement.
He loves them both.
That's good, because they can discriminate between the
Sure,
different
sure. So here is this is what makes it so interesting. Helmholtz says there is another constant of nature that we don't know yet. Say 573 atoms. I'm just making it up.
Yeah.
Below which Schrödinger holds, above which Newton holds. So there is a threshold
Yeah.
when you come to a single graviton, such that quantum mechanics will not work anymore. Zeilinger, on the other hand, says quantum mechanics is correct, period. You don't see chairs or human beings or cats being superposed because they are not isolated. So they are being measured by everything else. But give me the technology, put me in outer space when there is complete dark, no gravity and so on, and I can show you how cats can be superposed or even larger objects. It is interesting that Zeilinger is pushing the limit upwards, and he may reach Penrose's limit. We are all waiting. This is what makes quantum mechanics so exciting.
I got the impression from Roger that it's going to still be.
Yeah, no, it's the other Marcus.
Yeah, but Zeilinger said, yeah, this is his prediction. But Zeilinger says, if you help me just isolate it enough, so that gravity makes no difference, then everything can be. But Penrose actually says that if you try to superpose a chair, but even if there is no gravity, the difference, the gravitational difference between the two paths of this object outside of Earth is going to give a collapse. This is what makes it so interesting. When Penrose talks about gravitation, it's not the Earth's gravitation.
No. It's self-gravitation between the two.
You understand? You understand how?
Experiments have been done with molecules and things.
Yeah.
No departure from quantum theory has been detected. And my guess is that the experiments would not have been nearly sensitive enough for the sort of effects that Roger's talking about.
I suppose because I'm familiar with all that, and I suppose it was just the architecture of this experiment here, where the paths are long way apart. So if you, what he said, one way of looking at it is how much work you have to do that whole part, and I suppose it
Avi, I have another question. I just wanted to stick up a little bit for Einstein as a lover of quantum mechanics, not only a hater of quantum mechanics. Because when you said, and I realized this was for dramatic effect as well, that Einstein would have said for sure the photon is either this way or that way. I think Einstein would have said it's perfectly permissible to write down a quantum state of a superposition, but he would go further and say that perhaps there was something deeper, that there was another layer of the physics we had to be to uncover. I don't think he would have objected to saying that the photon is in a superposition of the two paths. Would you agree with that or not?
Conceded defeat on this. For several years, he was hoping to show that this is wrong. When he saw, I showed how you place detectors which do not absorb the particle and let it continue. And then Bohr showed to him that in such a delicate experiment will reveal real superposition. Then he gave up. Then he waited for a few years, and then he came with the EPR to show that there is a clash with relativity. So he was trying to defend classical physics ditch after ditch, and he knew when to withdraw. But for the rest of his life, he was hoping to get a better theory, such that if it does not revive determinism, at least the idea of objectivity, that particles have objective properties.
Yeah.
This, I believe, that he was hoping to do till the last day of his life.
Yeah.
Today, what he would say with new advances, I think that he would take a completely different path.
All right, why don't we thank Avi for this story?